Buenos días, mi nombre es Carolina Salinas Thompson y voy a presentar el trabajo elaborado.
Good afternoon, dear colleagues. My name is Kwanish Samarkhanov, and I'm representing National Nuclear Center of the Republic of Kazakhstan. Also, I'm a third-year PhD student. First of all, I would like to express sincerely gratitude to the organizing committee of the conference. My today's report is devoted to the development nuclear excited source of coherent and incoherent radiation with the direct nuclear pumping. Today's report is something like a brief overview of our investigations. I will try to give you an information about the results we obtained, conducted at two operating research reactors. The slides on the left shows neutron nuclear reactions used suitable for gas media excitation. Nowadays, two possible methods of gas media excitation are known. The direct pumping of gas media is carried out as a rule by the nuclear reaction products with thermal neutrons, such as uranium fusion fragments, helium-3, or with boron-10. Less studied was the use of nuclear reaction of lithium-6 with thermal neutrons. The main goal of our investigations is to study the possibility of obtaining laser action at PS transitions of noble gas atomic upon excitation by lithium-6 and alpha-tritium nuclear reaction products. Stationary, the IVG nuclear reactor was used as a thermal neutron flux source to implement of lithium-6 and alpha-tritium nuclear reaction and gas medium excitation. Several modifications of experimental devices with lithium have been developed and successfully tested. Today, I wanted to pay attention to the results of one of them. The impile experiments on study luminescence of gas media were held on the Lyana test bench located in the IVG-1M reactor hall, occurring non-coherent optical radiation in the volume of the device during the impile tests outputted from the reactor core using 10-meter fiber optic cable. Remote recording of luminescence spectra was carried out by an operator using an optical spectrometer. On the right-hand side of the slide, you may see conditions of impile experiments. There are some results with the unary and binary gas mixtures, argon-krypton, krypton-xenon, argon-xenon, to be more precise. Studying the luminescence of binary noble gas mixtures, we found that the temperature of lithium layer above 500 Kelvin lithium lines, as well as sodium potassium lines, appears in the spectrum. The temperature dependence of the luminescence in binary mixtures was studied. The intensity of main atomic lines and the molecular band monotonically decreases with increasing temperature. The appearance of lithium lines and impurities of sodium, potassium is associated with vaporization during the release of nuclear reaction products from the lithium layer. Molecular bonds observed in the emission spectra of paired mixtures were identified as transition between the states of heteronuclear ion molecules. Here you may see the main plasma chemical reactions. A rapid growth in the luminescence intensity is well approximated by this equation. Apparently, the main channel for the excitation of alkali metal atoms is transfer of excitation in the process of collision of noble gas atoms in the first stage with alkali metal atoms and subsequent ion molecule processes in the plasma. So our investigations are ongoing and carried out on the second research reactor, so-called IGR nuclear reactor, which has the highest value of thermal neutrons flux in the worldwide. So you may see technical parameters of the reactor, optical, to conduct in-pile reactor experiments. A special experimental facility was developed and constructed. The experimental facility functionally includes in-pile experimental device, a gas vacuum system, information and measuring system consisting of system for registering and controlling the temperature of the device, and the system for recording and optical radiation. So optical radiation occurring in the volume of the device was focused by a flat convex lens mounted of the device and outputted from the reactor room by a 25 meter fiber optic cable. Further, the signal was from the fiber optic cable was divided using bifurcated fiber into 4 channels. To the input of the silicon photodetector and indium gallium arsenide photodetector. The signal from the photodetector was recorded using Tektronix TBS oscilloscope. The emission spectrum of the gas medium was recorded using QE optical spectrometer using SpectraSuite license software. The recording system allowed reliability capture even spontaneous emissions coming out through the resonator mirror to record spectral and temporal characteristics of the optical emissions. So you may see a preparation of the optical system registration for in-pile experiments. Figure on the left-hand side presents the design of a nuclear excited source of coherent and incoherent optical radiation with direct nuclear pumping. Lithium serves as a source of laser mixtures pumping with products of lithium and alpha tritium nuclear reaction, but also effectively deactivates lower 1s levels. During the in-pile experiments at IGR nuclear reactor, thermal neutrons bombarded the lithium layer. The alpha particles with a kinetic energy of 2.5 mega electron volt and tritium ions with a kinetic energy of approximately 3 mega electron volt generated in a few seconds via lithium-6 and alpha tritium nuclear reaction excited the gas medium. So you may see fabrication and tuning steps of the experimental device with mirror system. Here you may see presented in this slide. So about the experiments we obtained, helium-xenon mixture was used to reach the laser action. An in-pile experimental device with a mirror system was irradiated in a burst mode with the duration of 0.13 seconds and the thermal power of the IGA reactor equal to 9.5 gigawatts. As a result of the in-pile experiments of spontaneous emission spectrum and the oscillograms of signal from photodetectors we recorded. As can see from emission spectrum, only lithium lines are present in the emission spectrum of helium-xenon gas mixture, but Diana test bench located in the IVG-1M reactor hall, occurring non-coherent optical duration of 0.13 seconds and the thermal power of the IGA reactor equal to 9.5 gigawatts. As a result of the in-pile experiments of spontaneous emission spectrum and the oscillograms of signal from photodetectors we recorded. As can see from emission spectrum, only lithium lines are present in the emission spectrum of helium-xenon gas mixture, but xenon lines are absent. So the threshold of laser action at the xenon atom transitions wasn't reached. The signal from photomultiplier and photodetector are approximately proportional to the reactor power. There is no threshold dependence on the pump power, which is characteristic of coherent radiation. There is some conclusions. With your permission, I will not read everything. So in my report, I present the results of in-pile experiment to investigate spectral and temporal parameters of optical radiation during the excitation of gas mixtures by products of lithium-6 and alpha-tritium. So the generation threshold wasn't reached during irradiation conditions at the IGA reactor. So the reasons for the absence of coherent optical radiation are currently under discussion. There is also of interest in terms of clarifying the mechanism of population of atoms, of noble gases, lithium with excitation by radiation, developing models that allow describing the processes of generation, diffusion, and the release of tritium ions and alpha particles from the near surface layer of lithium during neutron irradiation. So thank you for your attention. If you have any question, do not hesitate to contact me by the following email address. Thank you. Good afternoon, dear colleagues. My name is Kwanish Samarkhanov, and I'm representing National.
Good afternoon. My name is Rogério Figueiras. I'm from Federal University of Rio de Janeiro, and I will present the work G1302 entitled Preparation and Homogeneity of Monazite Sandy Matrix Candidate Reference Material for Activity Concentration Measurement of the following radionuclides: potassium 40, radio 226, radio 228, and lead 214. Thank you very much for attending my presentation, and let's get started. I bring some philosophical questions. What does it mean to measure something? How can we quantify the accuracy and precision of measurement? This is important questions mainly in nuclear field because we make statistical measurements and it is important the precision and the accuracy of the measurements. So, metrology is an important subject in nuclear field. Certified reference material, CRM, are a type of control, or as known as standard. They are indeed for analyzing or testing. These standards is followed by a certificate with one or more proprietary value, certified by a procedure that establish their traceability to obtaining an exact unity in which the proprietary values are expressed. Certificate values accompanied by an uncertainty for an established level of confidence. Confidence is an important question in this work. It's not make sense make many works if you can trust in this measurement of the activity. CRM have multiple uses in the laboratory, such as calibration, metrological control of the equipment, verification and accuracy and precision of analytical methods, validation of the methods, and quality assurance of results. CRMs are scarce in general, mainly in nuclear field. So we have many difficulties to obtaining CRM from different metrics. So it's important to develop new CRMs, but it's a laborious process, and so I think because they are scarce. Homogeneity is the most important characteristic, and it's very difficult to obtaining. In this work, it was our biggest challenge. We try to use Dosimetry, but the material is not homogeneous, and so we needed to mill this sanding for obtaining the homogeneity. Brazil is among the countries with largest and most important deposits of this mineral on the earth, monazite sands. We can find these sands enriched by thorium in Areia Preta Beach. Although these sands have no scientific interest, we don't have yet a CRM for these types of metrics, of sandy metrics, black sandy, monazite sandy metrics. And so we decided to develop this standard. We think it's important to have this kind of standard, and mainly to dominate the methodology to obtain CRMs. So this work aiming to study a candidate of a CRM in natural radioactive sanding. And as I told you, we face a question about the heterogeneity of the sand. Simply don't work if you put the sands in recipient without meal, because the granulometry is an important parameter in this case of this kind of sand. This slide shows the sampling collect. We collect the sand in the middle of the beach in 3 points, one a little bit more closer to the water, another one a little bit more closer to the road, but in the middle of the beach. We start the first 30 centimeters of sanding to avoid garbage and organic material. We collect about 40 kilograms of sanding. It was collected on February without rainfalls, at least 1 week before a rainfall. So this photographic shows the real time when we collect these samples. After that, the sand was ground at 318 RPM for 20 minutes in a ball mill equipment, this one that we can see. So it's an important step in the methodology. After drying, washing the samples, they are put in the jar or recipient with a cap that have not good screw, and so this jar are closed, and we put a wrap type in the perimeter of the cap, and so we put the jar in wrapping in a film, in a PVC film, and so we leave the samples to rest about 30 days to reach the circular equilibrium. This methodology is not ordinary in this field to measure the radio 226, and so we do that, and the step before is to take measures on the germanium hyperpure on our laboratory. The samples were measured on this detector of the photographic. The measure taking 6 hours, and we have done 3 measurements in each pod sequentially in order to minimize the interference in the repeatability. So the result was compared by the soil standard by ERA. We used this to make the control of the measurements. This is the activity concentration of the samples. We can see the potassium 40. We have a little bit of the variability in the results. Radio 226, it's a good result. We don't have a big variance. Same as the radio 228. We can see the values much higher than the radio 226 because, as I mentioned, this is the area that's an anomaly of the thorium, and the lead 214 have the good results as well. We can observe these results having a good correspondence with radio 226. In fact, is shown a good circular equilibrium because these radionuclides have the same chain of the Kaiman, and so it expects that they have the same value. This is an important result that shows that our setup of measurements are really reliable. The potassium, we expect as well this more variability because the efficiency of potassium on this energy is a little bit low. You don't have a good efficiency on in high energies. Another thing is that the potassium have a probability of decaying only about the 10% and not too high. And so I think the both of this characteristic of the potassium that making it's a higher statistical variation in the measurement of this radionuclide. And so I think because the potassium is the worst of the on this measurement because the statistic is a little bit poor compared with another ones. This is a result of the homogeneity study with ANOVA test. We can see the result. We can see that radio 226 and 228 are very close results. It's important. The lead, I think, is the better of the all radionuclides. I think is the lead having a good efficiency of our detector on this energy, about 300 keV. And the p-values as well, the roast is the potassium, because I think this parameter of the I told about the probability of decayment and the efficient that we have an important statistics for this radionuclide. The F calculated was 5.15, and all of radionuclides is above this number that show us that have a good homogeneity, and so is this result of our work. This is the uncertainty of the homogeneity. We can see one more time potassium 40 with the higher uncertainty between the another radionuclides. One more time the matter was lead, and radio 226 a little bit better than radio 228. This slide shows a comparison between the raw sand in nature sand, when the granulometry have a big influence on the results, and the treated sand. Treated sand, that I mean reading sand. So we can see clearly the coefficient of variation really higher in the raw sand when we compare with the ground sand. We can see in the radio 228 a big difference. This difference was big even in the variation, but in the measurement of the concentration of activity is a little bit. It's really different after we grading the sand. So this is the result. We can see here that its granulometry is a really important thing on the homogeneity equations. Finally, this is the conclusion of our work. We have a good homogeneity measurements in this time. The concentration of activity of the radionuclides are these one with the uncertainty of the average of the pods. And after the certification, the MRC will be used for calibration, quality control, method validation, and precision and accuracy in gamma spectrometry, monazite sand on our laboratory and other laboratories that we will distribute the MRC in Brazil. So this is the reference that we use. I would like thanks for the attention of this presentation, and I am available for doubts and comments. Thank you very much.
Hello, this is Uma Muslima, PhD student at Sano University, Malaysia, and my original country is Bangladesh. Here I will present the tempered glass of a smartphone as a potential media for thermoluminescent dosimetry. In this presentation, I will briefly discuss about the ionization radiation, thermoluminescent dosimeter, dosimetry characteristic, dose quantities, and the studied material smartphone tempered glass. Radiation that causes ionization is called the ionization radiation. And there are different types of ionization radiation. It can causes from alpha particle, beta particle, X-ray, gamma ray actually. And these ionization radiation can be used in different ways as diagnostic and treatment in industrial manufacturing, consumer product, safety and security, electrical power generation, and also in the spacecraft power supply. But this ionization radiation also causes defect to the human body as well as the human cell, because in human cell there is also mitochondria, nucleus, and in nucleus there is DNA. And when ionization radiation affect the DNA, it will split up, and this splitting up of DNA will cause the immature growth of the cell that can cause cancer, tumor, etc., which is very harmful for the human body. A person can safely receive ionization radiation up to 100 millisievert in a consecutive 5 years period, but of course it must be not more than 50 millisievert in any calendar year during 5-year period. And here is a chart for whole body and different parts of the body actually for different age limit. But there is also different types of dose. That means absorbed dose, equivalent dose, effective dose. The per unit mass of substance in gray is called the actually absorbed dose, and the equivalent dose allows different types of ionization radiation to be considered equally with respect to their potential to cause harm. And different tissue and organ may vary in how they respond biologically to a given type of radiation is called the effective dose. So the determination of absorbed dose or dose rate resulting from the interaction of ionization radiation with matter is called the radiation dosimetry, and the meter and the dosimeter or a device which measures the above radiation dosimetry. That means the device that measures the radiation dosimetry is called the dosimeter. And our target is to develop a low-cost, easily available dosimeter for environment purpose. That means the retrospective dosimeter. So here we will discuss about alternative dosimetry, and the material we have chosen as the smartphone tempered glass. This material has chosen because of their moisture resistance, transparent media, fast sample preparation, and easily available with low cost. We have chosen different types of smartphone tempered glass of different phone which are easily available in the market. They are the branded. They can be used for the phone branded with Samsung, Huawei, Xiaomi, iPhone, etc. And their types are defined actually. According to their types, we have labeled them as the sample number A to F, and they are actually curved tempered matte glass, big curve auto absorption glass, HD anti-pip tempered glass, large duct anti-dust HD glass, S to S curved glass, curved matte glass, blue. So our research objective is to study the dosimetry properties, the TL curve, dose response, linearity index, sensitivity. Also, we want to analyze the elemental analysis with the ACM EDS analysis, and after the analysis with above technique, we can conclude the material as a retrospective dosimeter. To do that, to analyze the characteristic, the methodology will be subdivided into some part that are sample preparation, annealing, sample irradiation, till measurement, and also the ACM EDS. We have prepared the sample from the intake glass sample. At first, the blue sticky part of the sample, tempered glass was removed by simply pulling, and then the glass was washed by acetone to remove the extra glue from the glass. And after that, we have cut the glass into 5 by 5 millimeter square size with a diamond cutter. And then to remove the history of the radiation, previous radiation, we have annealed the sample with 400 degrees Celsius for 1 hour. And we have irradiated the sample with photon irradiation at 2 to 10 gray, and the energy was 6 MV with a linear accelerator. And we have after that we kept the sample with in a black box to avoid the extra light exposure, and we use 3500 Harshot real reader with wind and software to measure the till parameters, and the parameters and the temperature heat was set 10 degrees Celsius per second, and the reader temperature was fixed to 400 degrees Celsius, and the preheat temperature was 550 degrees Celsius. Then ACM EDS analysis was also analyzed, and within that we have also calculated the effective atomic number. So after readout process, we have find out this TL glow curve, and the TL glow curve actually defines the intensity of luminescence as a function of temperature, and the area under each graph represents the number of electrons released from trap, and thus by association the radiation energy deposited. The glow peak maximum indicating the maximum number of electrons released from the trap. Here from the graph we can see that the peak of the all sample remain within the 125 degrees Celsius to 300 degrees Celsius, and the peak temperature of individual peak lies within the 180 to 250 degrees Celsius, which is quite good to be a dosimeter. Here's a graph for dose response. In this graph, we have plot this graph for doses 2 to 10 gray at 6 MV photon energy, and we can see from the graph that it shows quite linear response for all samples, and among all samples, SD NTP sample shows the good linearity. The R square factor is 0.99. To be a good dosimeter, linearity is a must term. And we can see that our all sample shows also the on sample named SD NTP shows the good linearity response. We also analyze the sensitivity to show the sensitivity within the dose. In this case, we have chosen doses from 2 to 10 gray at 6 MV photon energy, and we can see that SD NTP sample shows good response with the dose, and also among other sample, and also you can observe that at 2 gray the sensitivity is high, and within the dose sensitivity of the all sample getting low, but SD NTP sample remains quite stable within increasing the doses. This is a graph for linearity index. As you can see from the graph that at 2 gray, all sample shows linearity index is 1. That's mean linear. And within the increased dose, we can see that all sample shows sublinearity characteristic. This graph will define whether the sample is energy dependence or independence, and from the graph we can see that from 6 MV to 10 MV the intensity remains same, but so we can say that it is energy independent. The ACM EDX result shows that there is a huge abundance of oxygen among other constituents. Silicon and carbon is also present here, as because silicon, oxygen, carbon is the main constituent of the glass material. Other element is also here. This is because to lower the melting temperature and to improve the glass properties. Using the ACM EDX analysis, we have calculated the effective atomic number using minor equation. This is the crucial for determining the suitability of material in medical or environmental or industrial dosimetry. And we can see the value of the effective atomic number and can conclude that the effective number is aligned with the bond. So we can say that material is potential candidate for dosimetry application. Finally, after the overall presentation, we can conclude that as the effective atomic number is close to the human bond, that makes the material ideal to be a good dosimeter, and the glow curve between 125 degrees Celsius and 300 degrees Celsius, and the maximum peak between 175 to 250 degrees Celsius, which is good for dosimeter. And among all samples, HD anti-peak tempered glass, which can be used for iPhone 14 and iPhone 14 Pro Max, reveals promising TL dosimetry properties for photon radiation and can be used for retrospective dosimeter. Thank you for your kind attention, and below is my contact information for the further query. Thank you so much.
Hello everyone, you hear me? Yes. Okay. Hello everyone. I am Wisal Bushra Hassan Ahmed, Assistant Professor in Medical Physics, Taif University, Saudi Arabia, College of Applied Medical Sciences, Radiological Sciences Department. Firstly, I would like to thank the conference organizers for their acceptance to participate in this important international conference. I will present our research titled Radiation Dose Assessment of Medical Staff in King Faisal Medical Complex and Adherence to Radiation Protection Practices. Please, next slide. I can control. Yes, this is our presentation outline. I will start with the introduction. Ionizing radiation can lead to adverse health effects to medical staff. So, to minimize these effects, regular monitoring of radiation dose is essential to maintain the occupational radiation exposure as low as reasonably achievable, a LARA principle. Also, adherence of medical staff to radiation protection in practice. The annual effective dose limit for radiation worker is 20 millisievert, recommended by International Commission on Radiological Protection. Yes. Our aim of the research is to determine the effective dose for medical staff in King Faisal Medical Complex in Taif City and to evaluate the radiation protection methods in practice. To do this, there are subjects and methods. Firstly, the study examined the thermoluminescence dosimeters record of 50 medical staff work at King Faisal Medical Complex through 2 years, 2019 and 2020. The radiation doses were monitored by using skin thermoluminescence dosimeters or thermoluminescence detectors present in Riyadh city. Also, a questionnaire was applied to the medical staff to evaluate their radiation protection methods in practice. Our results from this research were presented in tables and figures. In table 1, the mean annual effective dose in 2019 is present, and the mean annual effective dose, yes, it was 1.1 millisievert, and in 2020 the mean annual effective dose for medical staff was 1.46. In this table there are two maximum values recorded for the medical physicist and radiologist here, which was 7.2 in 2019 and 2.6 in 2020. This maximum value is explained as miscorrect of using TLDs. It is not the exposure dose to the medical staff exactly, because those medical staff has a value of effective dose in the next months of the year. They are present and they are working. So it is the using of thermoluminescence detector by those medical staff. In figure 1, show us the distribution of annual effective dose in millisievert according to gender. The mean annual effective dose for male is greater than female in 2019, and there is increase in mean annual effective dose for male and female in 2020. Figure 2 show us the distribution of mean annual effective dose in millisievert for medical staff in 2 years, 2019 and 2020, according to job, medical staff job. It represents, it shows us that the doctor mean annual effective dose in 2 years, same, but the mean annual effective dose for the medical physicists increase in 2020. Figure 3, the result in figure 3 show us the adherence of medical staff to radiation protection practice, which show us the less adherence is wearing of medical staff to for gonad shield, and the adherence of medical staff to alarm principle is adequate. Also, all medical staff or the high percentage of medical staff adherence to wearing the thermoluminescence dosimeter during their work. Our conclusion from this research, according to this research finding, the mean annually effective dose for medical personnel in King Faisal Medical Complex was well below the prescribed limit, and the compliance with radiation safety alarm principle was satisfactory. We have recommendation. This research recommended conducting a systematic sampling of thermoluminescence dosimeter recording from the 2018 to 2023 in all hospitals in entire city to obtain representative sample of the population. Also, it recommended increasing the sample size of the questionnaire to obtain more accurate and comprehensive data. This is the reference that we use in our research. And I would like to thank firstly King Faisal Medical Complex for their assistance in the research. Also, I want to thank Prof. Hamid Usman for his helping to participate in this important international conference. This is my contact. If you have any question, you can ask via this contact. Thank you for all.
Greetings, my name is Júlio Diniz Ramalho Prado, and I'll present the work done on the paper titled Study of the Gamma Radiation Fields of Irradiators in a Calibration Laboratory Using Monte Carlo Codes. The paper was authored by me and by Marco Aurélio de Souza Lacerda. We're both affiliated to the Centro de Desenvolvimento da Tecnologia Nuclear, which is a nuclear technology research center in Brazil. So, a dosimetry calibration laboratory of the CDTN recently acquired a new gamma irradiator. I'll be referring to that laboratory as LCD from now on. So, the new gamma irradiator in the LCD is a Hopewell Designs Model G10, and its higher activity source is a cesium-137 source with a nominal activity of 1.85 terabecquerel. The previous gamma irradiator in the facility was an STS model OB85/3, and its higher activity source is a cesium-137 source with an estimated activity of 740 gigabecquerel in 1997. So it was necessary to characterize the gamma radiation field of the new radiator. So we chose to use computational methods first, and therefore we used Monte Carlo codes so that we could gather relevant operational information such as radiation levels in rooms adjacent to the irradiator and the need for changes in the irradiation room due to scattered radiation. So this paper presents modeling and simulations involving the irradiators, including models that simulate the entire laboratory building in order to obtain air kerma and ambient dose equivalent rates. Less complex simulations, for example with point sources, were also carried out. The computer simulations were validated through experimental measurements with calibrated ionization chambers. So, in the materials and methods section, we have the STS, OB85 and Hopewell G10 irradiators. The relevant sources are the aforementioned higher activity sources of the irradiators. The Monte Carlo codes used were MCNPX version 2.7.0 and FITS version 3.26. So this is the plan of the first floor of the laboratory with its area monitoring points. The laboratory was fully modeled on MCNPX, and the area monitoring points were used when assessing radiation levels in rooms adjacent to the irradiation rooms. So these are the irradiation rooms. This is where the Hopewell G10 is placed. So there we go. The air kerma and ambient dose equivalent rates were determined at different distances, simulating various cases and situations. So we simulated cases A to Y. With MCNPX, the tallies used were F4, F6, and plus F6. We used a photon-only tracking mode and a photon and electron tracking mode. With FITS, the T-track and T-deposit tallies were used, and cases D to Y were modeled and simulated only on MCNPX. So, this figure represents the basic setup of the simulations in cases A to E. So there's a sphere with a radius of 450 centimeters filled with air. The source is in its center. The cells with tallies are also spheres with a radius of 2.5 centimeters, and they are also filled with air. We simulated 5 times 10 to the power of 8 stories in those cases. So, in the simulations involving irradiation room walls, a complete LCD model was used. The number of simulated stories was 10 to the power of 9 minus 1. Variance reduction techniques were used, and radiation levels in areas adjacent to the irradiation rooms were assessed. Dosimetry of the irradiation field of the Hopewell G10 irradiator was carried out without attenuators at distances of 100 and 200 centimeters from the aforementioned source. A PTW ionization chamber model TN32002 was used. Those measurements were taken at 3 points in areas adjacent to the irradiators using the Hubble-Gitane irradiator with the aforementioned source without attenuators. The points assessed were point 6, F1 and F2. So point 6 is here, point F1 is here, point F2 is here. A reticle ionization chamber model 10X6-1800 was used. So we're now in the results and discussion session. And on the following tables, the Kerma columns provide results from Tally 6 and from Tally T deposits, which give us the average contribution to the air Kerma caused by each photon emitted by the source. Considering that we use photon-only tracking. And the H10 columns provide results from Tally 4 and Tally T track with pins and multipliers. So that gives us the average contribution per photon to the ambient dose equivalent. And the error columns provide relative errors for each value. So these tables show the results from MCNP and FITS for cases A, B, and C, which are the isotropic point source, collimated point source, and volumetric point source. The volumetric point source simulates the capsule found in the Hubble-Gitane irradiator. And this first thing that should be pointed out is that there are differences between the values given by the codes. So the highest differences found between values for Kerma and H10 given by MCNPX and FITS were respectively of 10.9% and 10.5% for Kerma and H10 values. It's also worth pointing out that using a collimated point source reduces the relative error compared to using an isotropic point source, and that using the capsule as a source reduces the Kerma compared to the point source at most by 23% in both, approximately 23% with both codes. So, using the values given by both codes for the isotropic point source, we were able to calculate the air Kerma rate constant and the ambient dose equivalent rate constant. And as you can, we also compare them with values provided in the values provided in the literature. And the FITS code, as you can see, provided values much closer to the values available in the literature. So this table now shows us results from case E, which simulates the irradiators with their capsules, but without any walls surrounding them. So we compared the results from case E to the results from case C, which is just the capsule. And we can see that simulating both irradiators at the same distance from the source, the Kerma values are higher in case E than in case C. So to explain that, we created the hypothesis that there is scattered radiation within the irradiators. And to support that hypothesis, we analyzed the photon fluency spectrum at 100 centimeters from the sources in case C and E, simulating only the Hubble-Gitane irradiator, both if in a photon-only tracking mode and a photon and electron tracking mode. So what I can see is that there's a higher difference between the cases when assessing the lower energy, lower energy photons, which does support the hypothesis that there is radiation being scattered within the irradiators. So this table presents analogous cases, so like cases with an isotropic point source, a collimated source, and a volumetric source, but with and without laboratory wall, ceiling, and floor. So, case A is analogous to case F, but case F has the laboratory wall, ceiling, and floor. And as you can see by the difference between the cases, there is radiation being scattered on the walls of the laboratory in the cases with isotropic sources, also including the volumetric source. But with the collimated point source, which better represents the irradiator, there isn't such a problem. There doesn't appear to be radiation scattered on the walls of the irradiation room. So, case I is the most important case for this work because it simulates the Hoplogetane radiator with its source inside the radiation of the laboratory. So these were the Kerma and H10 values simulated inside the irradiation room, and those values will be used when calculating the air camera rates that will be compared with the experimentally measured air camera rates. So, in terms of the simulation, assessing the H10 in areas adjacent to the irradiation room, simulation only the Hoplogetane radiator, I should point out that the Hess values found were in points 4A, right in front of the irradiator, which is to be expected, and points F1 and F2. So, now let's talk about the experimental results and talk about the Hoplogetane dosimetry at 100 and 200 centimeters from the source. So the table shows the measured camera rate, its combined standard uncertainty, and the simulated camera rate, and the difference between the measured and simulated values. And as we can see, the simulated values are within 1.84% of the measured data. So these tables show compare the measured dose rate and the simulated dose rate, and the measured camera rate and the simulated camera rate at the area monitoring points as shown before. So these are points 6, F1, and F2 as shown in the plan. However, here the differences between the measured and simulated values are too large. So, the gamma radiation field around the irradiator of the LCD was studied using Monte Carlo computer codes. Less complex simulations made possible to partly verify the methodology. And now regarding the Hoplogetane dosimetry inside the irradiation room, we can say that the simulations provide air karma and emit dose equivalent rates that were validated experimentally. The simulations carried out for radio protection purposes in areas adjacent to the radiation rooms could not be validated, both because some of the values had too large of a relative error, and because the experimental measurements did not agree with the simulated values. So we could suggest as a follow-up to this work to use other methodologies and variance reduction techniques. We could also do all the same work with the irradiator and laboratory modeling on the FITS code. So thank you for the attention. That is my email if you have any questions.
Profesor Epifanio,
Sí,
es su turno.
voy a
Ya puede
compartir pantalla.
comenzar.
Sí. Muchas gracias al comité organizador por la oportunidad de platicar. Y bueno, my special recognizing to Professor David Briley for his contribution to solid state dosimetry. Mi trabajo es sobre termoluminiscencia y fotoluminiscencia como propiedades de un vidrio que lo formamos en vidrio, luego lo llevamos a polvo para poder analizarlo, del borato de bario con disprosio trivalente. Siempre hemos buscado una buena sensibilidad de los materiales que respondan a la radiación, que tengan una estabilidad química, que no sean tóxicos, que tengan defectos estables para que sean interesantes de estudiarse. Hay varios ejemplos de ellos, entre los cuales está el borato de bario, en este caso que vamos a abordar. Los boratos en general son muy cercanos al tejido, al hueso o al tejido blando también. Siempre buscamos y estamos interesados en las propiedades ópticas, estructura de las curvas de brillo, el decaimiento de las señales de termoluminiscencia que involucran pues, el fenómeno de recombinación de defectos para lograr la emisión termoluminiscente. Hemos preparado este material de borato de bario, pues haciendo un melting, esto es fundición, tal cual se hacen los vidrios. Si hay una empresa interesada en hacer vidrios, bueno, este es uno de los materiales interesantes de analizar. En general, el fenómeno de termoluminiscencia, pues uno postula que este es un arreglo, bueno, es un trabajo adaptado del trabajo de Horowitz, Horowitz, de 1998, en el cual está hecho para el fluoruro de litio dopado con magnesio titanio, y en este caso, pues tenemos defectos que se generan cuando en la matriz de fluoruro de litio, una estructura cúbica, anexamos magnesio y titanio de diferentes concentraciones y se van generando estos pares de electrones atrapados en vacancias junto con las impurezas de magnesio divalente, y adquieren diferentes formas y estos dipolos en general, la estructura dipolar, nos van a ayudar pues a lograr una emisión termoluminiscente cuando esto se recombine. Entonces, gracias a la recombinación por calor, en este caso, lo podemos hacer por luz, lo que se conoce como luminiscencia ópticamente estimulada, o por calor llamamos termoluminiscencia. Y nos genera esta curva de brillo que está a la derecha, la cual obviamente que para el fluoruro de litio tenemos alrededor hasta de 11 picos, pero aquí, bueno, se muestran solamente 5. Desde luego que los materiales dependen mucho de su historia térmica, la forma en cómo se preparan. Entonces podemos trabajar con policristales, forma de monocristal, forma de polvo, en la forma de un film, tanto estructura nanométrica como micrométrica. Y están estos diamantes, las sales, por ejemplo, los cloruros, fluoruros, los cuarzos, feldespatos que tienen aplicación en dating del medio ambiente, y también los boratos. Hay varios métodos de preparación: la combustión, reacción de estado, vidrio. La síntesis para lograr el borato de bario lo hemos hecho con este melting method. Llevamos la mufla hasta 1000 grados y de ahí bajamos la temperatura ambiente. Y nuevamente hacemos el polvo para recristalizarlo a 600 grados durante 1 hora y sobre una superficie pues prácticamente tibia, que puede ser de carbono o puede ser una de cobre. Colocamos vertemos las gotas de este material para que se logren tener, como lo que se observa acá en la figura de la derecha, que son como unas perlitas de estos aretes. Prácticamente son vidrios transparentes de este color amarillo, están dopados con óxido de disprosio. Elegimos diferentes tamaños de partículas, se caracterizan por vibración de rayos X. Los pulverizamos, en este caso, para lograr meterlo a este lector termoluminiscente que se mira aquí en verde, el cual tiene un disco que va a irradiar con una fuente de estroncio 90 y lo lleva al mismo disco cuando gira, lo lleva a la otra posición del detector y va a emitir la respuesta termoluminiscente. Usamos también un espectrofluorómetro o espectrómetro de fluorescencia, el LS55 de Perkin-Elmer, para lograr las emisiones de fotoluminiscencia. Nuestro objetivo es estudiar la fotoluminiscencia y la respuesta termoluminiscente de este borato de bario. Como sabemos, el tiene varias transiciones, al menos 3 bandas principales, una en el azul, una en el amarillo, otra en el rojo. En general decimos que las transiciones, la 4F 9 medios, y de ahí van a la 6H, a sus respectivos colores. Si esas bandas logramos nosotros observarlas, ustedes pueden ver la primera transición de estos picos. Aquí estamos para diferentes concentraciones del dopante, el disprosio. Esto fue 0.1, 0.5, del 4F92 a la 6H11 un medio. Y prácticamente, gracias. En esta siguiente charla es una síntesis de la termoluminiscencia del borato de litio, también en vidrio, dopado igual con disprosio. Y bueno, en realidad estamos interesados en los defectos y pues en la preparación de los materiales, entre ellos el borato de litio, y siempre pedimos que tengamos una relación lineal cuya respuesta pues tenga un fading relativamente bajo con una buena reproducibilidad. Y del lado derecho arriba pueden ver ustedes cómo se forma el vidrio. Es un líquido viscoso, el cual nuevamente lo preparamos a 950 grados y lo llevamos a irradiación en este equipo ahora Lexis Research, que tiene una fuente de estroncio itrio 90. Y nuestro interés pues es esto, como depende de la preparación del material. Preparamos 6 tipos de muestras. Algunas de ellas le metimos óxido de aluminio o alúmina y a la otra le hemos metido dimetil
Buenas tardes.
ellos sí. No, ya lo tengo. Estaba en extenso. ¿Sí?